So before we get started, just some housekeeping notes. So there's no planned fire alarm for today. And additionally, it would be much appreciated if you could set your mobile phones to silent. Yep, so for our event today is the 7th session for the MOGE discussion series. So it's titled Slope Stability and Earthworks. And just to say a huge thanks to our series sponsors. So they are Bob McDonald, Geotechnical Consulting Group, Atkins Realis, Earthworks, COVI, and RGI. So for today's agenda, we will have 3 short great presentations by our guest speakers. So we have Professor Emeritus Professor Eddie Bromhead from Kingston University, and then we have got Technical Director and Fellow from Atkins Realis, Paul Novak, and we've got Geotechnical Engineer from COVI, Matthew Wells. And after that, we will have a Q&A session or discussion session, and we'll follow it on with announcement on future events at BGA or ECG. And then for those in person, we would go to a nearby park and have some food over there. Yeah, so before we head on to the first presentation, just bear in mind we are currently using Slido. So if you want to scan the QR code now, and you can pop any questions you have throughout the presentation, and we will look at that at the end of 3 presentations. Yeah, so without further ado, I'll invite Professor Eddie to give us the first presentation. Thanks, Eddie.
Thanks very much. Right, well, I don't think you can do justice to this subject in 20 minutes. I don't think you can do it in 20 hours or 20 days, really. Perhaps 20 years is good, right? I'm going to just talk generally about slope stability. And thank you for everybody who's turned up in this heat wave, or perhaps that's what Central London's like all the time. I'd sort of rather forgotten. Here I am. I have been on site. Look, there I am wearing a hard hat. So what about slopes? Well, you get slopes 2 ways, either by making it a heap or a hollow, and it can either be man-made. Does this won't point with it? So this is the laser pointer, right? It's going to be either man-made or natural. And what tends to happen when slopes fail, and the whole point is we don't want them to fail. When they fail with something that generally is called a landslide. Now, David Varnes invented a classification system for landslides, which is made up with a material descriptor and a major mechanism. And so his 3 materials were soil or earth, rock and debris, and the 6 mechanisms were there: slide, flow, fall, sag, spread, and topple. And the ones that you're likely to come across are the top 3. The other 3 are somewhat esoteric. And what is a slide? Well, here's a picture of a slide. Basically, the material that moves separates from the parent soil mass or rock mass and moves as a block, generally, or a few blocks, but not very many. If it breaks up into lots of blocks, which flow and mix as they move, then you have a flow. And if they fly through the air, you've got a fall. And that's a very simple way of classifying things. Now, the sag is something that, unless you work in a mountainous area, you're unlikely to see, because it's basically a slide which can't go anywhere because there's another mountain in the way. So all you see are these little faults appearing in the mountainside. Okay, I'm sorry, that little arrow seems to have moved a bit in the moving onto the format of this presentation. But sometimes you see quite a lot of mechanisms all at the same time. And here is one of nature's compendiums, the volcano, where you might have the edifice itself might slide through the volcanic deposits, or involve the foundation as an Etna, where there's a bit of coast erosion as well, or you might get a flow of lava or ash. And so there's slides and flows, or you might get rocks which fly through the air, which their starting mechanism is perhaps not the same as a gravity-driven fall, but the end result, if one hits you on the head, your hard hat doesn't keep you safe, I'm afraid. It's just like a fall. Now, there's an extensive literature. Bloody hell, I've contributed to it on numerous occasions, and mostly the analyses of slope stability are all done in 2D. But nature doesn't read those papers. Nature insists that everything is three-dimensional, and yet the number of three-dimensional analyses which have been successfully done is really quite small. So the reason they say that three-dimensional is safer than two-dimensional is they always analyze it as a cylinder with flat ends. And nature's not like that for a whole set of reasons. There's geology involved. There may be cross-slope dips in the strata involved. The slope may have limited extent, like a volcanic cone. The movement, in fact, may not even be in the direction of the steeper slope. It can be slightly sideways. And there may be a three-dimensional variation in the fluid pressures that drive instability. So you can find out about slope stability analysis in dozens of books. The fundamental problem is you simply do not know what the properties of these materials are. I've sketched here three tests, which could be shear box tests, and fitting a straight line through the data. It's not a straight line. Anybody who gets a lab result from some testing lab that has 3 points that exactly line up in a line, they've fiddled it. Right? And then you get to, if you shear things far enough with something with a ring shear, then you might get 3 points which allegedly line up again. And once again, if they do line up, it's been fiddled. What I find is that I like to have at least 6 points, and I put a best fit line through it and also get the standard deviation, which is pretty important. Now, why do you not get straight lines? And the answer is because you never test the same material. If you take a section of a borehole log, you might have sample 1 is in this material, sample 2 is at the junction, sample 3 is deeper down. Or even if you take 3 small samples in a U100, there may be some dip in there, so they're never absolutely identical. So we simply don't know the properties. That's interesting enough. The other thing we don't know is the pore pressures or fluid pressures in the slope. So what I've done is I've done a whole bunch of cartoons here of the sort of scenarios in which slope stability can be important. You might have a spoil heap that fails. You might have an infrastructure embankment where the failure is either through the embankment fill or through the foundation. It's terrible if you build something on an existing landslide. And even if you just build it on sidelong ground, you might get water ponding up and then through flow that you didn't imagine. You might build something with dreadful internal features if you're unlucky to meet somebody who really doesn't understand about soil mechanics. Weather may have an influence. Submerged slopes are particularly difficult, and when you get drawdown, they're very, very difficult to deal with. And you may get construction-induced water pressures to deal with. So I couldn't do cartoons of hollows and cut slopes that hadn't failed. So here's one with a nice compound landslide with a basal shear surface running along a weak bed. If you want to know more about those, then consult QJ ECG in my Glossop lecture paper. There's a very interesting case where you've got a couple of these slide-prone horizons in the sequence, and then you get a system. This upper one, when it moves, drops the material onto the head of the lower one and can force it to move forward in a surge. Have to be careful about that. You have plane failures if the strata dip. And here I've drawn the spread. Now, spread is a nonsense. I'm sorry, David Vance, it is a real nonsense because it's either a slide or it's a flow. and it's just got a long run out. And the real problem with them is either they're so big that nobody can sink a borehole through them, or they're so runny that you wouldn't even get a drilling rig on them without it sinking in. So in this slide, I put a number of things for you to think about. First of all, what about earthquakes and static and seismic liquefaction? Liquefaction sometimes happens just statically. If you're building and you generate pore pressures and you've got a very weak core in a dam, for instance, the whole thing might liquefy. The Americans are terrified about that, and there's a very simple answer: don't use materials that liquefy. But they won't be told because they're Americans and they know best. Sorry if there's any Americans here tonight, so I can rubbish them. Right? Okay. Then something which is terribly important is the flow of water, which might cause erosion of particles. Now, this is not dealt with, as far as I know, in any soil mechanics textbook, but it's really quite important, and I'll show you an example later on. But surface water, for most of us, we encounter with overland flow that erodes material and gives us some sort of, usually a debris flow. And we mustn't forget the influence of waves with coastal erosion. And we mustn't forget that not only do we eat into slopes, but we also remove the foreshore, make the slope higher. And then, of course, we get underwater landslides, and they can be driven with wave loading and unloading with long wavelength, high amplitude, storm-driven waves. I've just chucked in this PhD student here. She studied underwater landslides. She was pretty good on the fieldwork, I can tell you. But when she came to lectures, she was a right pain because we had to have this big, like a bathtub, full of salt water for her to sit in. And getting her around from lecture theatre to lecture theatre, that was a nightmare. But anyway, she's off somewhere in the Gulf of Mexico at the moment, studying failures in the Mississippi Delta. And I haven't heard from her recently because her mobile phone packed up and she took it underwater. Right. So how do we analyze slope stability? Well, the answer is in one of two general ways. A limit equilibrium you've heard about. It's a sort of variant on plasticity theory. All we need are two things: a stress field, which doesn't even have to be very good, and a mechanism. And because the failure surfaces are normally curved, because this is what the stress fields in slopes give us, then we get a plasticity answer. And because the shear strength is largely independent of the stress path followed, the shear strengths we get, such as they are, aren't all that bad. I mean, they're not right, but they're not all that bad. So I've just put the factor of safety as a function of cohesion, friction, unit weight, pore pressure, slope, and height. But if we go to the continuum methods, which have infested a lot of modern thought, then we need so many more parameters. We need the pore pressure parameters, A and B. We need everything strain dependent, the modulus and the Poisson's ratio, or shear modulus and bulk modulus. And we have to follow the right stress path. Why? Because if we don't get anything like the right deformations. And I've read oodles of papers in Geotechnique and elsewhere where people keep factoring the properties, and that is not following the right stress path. So the resulting deformations you get, doesn't matter whether you use Plaxis or Crisp or Lussas or whatever, are just wrong, right? And the other thing about these numerical methods is that whereas there's plenty of software for limit equilibrium that you can test one program against another, everything in the continuum method uses a different algorithm, uses a different underlying theory, so you can't validate one against the other. And when it comes to EC7, well, I think you'll hear from my colleague that he don't think much of it. Well, I don't either. And one of the real problems is that pre-factoring the properties may lead you to finding the wrong failure mechanism. If you find the wrong failure mechanism, you will not design the correct remedial measures. So EC7 just drives me blooming bonkers, right? And The other thing is there's two criteria. One is to take the strength that 95% of your test results will exceed. That's 2 standard deviations below the mean. How many tests do you need to work out the standard deviation? Well, I've done work with students, and we've done 30, 40 tests, and we find that the standard deviation is about 2.5, 3 degrees. So that means that when you've done a test and you've got a line, take 6 degrees off it. And if you've done a residual strength test and you got 10 degrees out of it, and you take 6 degrees off that, you'll never, ever make anything work. So the other thing is, it says, take the worst possible pore water pressure conditions. Well, if you do that, what does it tell you to do in the way of remediation? Well, drainage, obviously. And then you go out on site and you put the drains in and no water comes out, and you haven't affected it in any way whatsoever. So be a bit careful about EC7 is the best thing that I can say. That's the 2 standard deviations. Right, so now I'm going to ask you, tell me the answers to this problem. Right, here's the first problem. Mr. Uphill has a house, right? And he's living there happily for 10 years. And Mr. Downhill comes along and excavates into the bottom of the slope and builds a house, right? It takes a year to get built. And then he's quite happy there for a year. And then Mr. Uphill decides he wants a flat garden. So he then puts some fill on the slope. And 2 years later, it fails. Who's responsible? Who caused it? Mr. Uphill or Mr. Downhill? But the answer is, if you believe that the last straw on the camel's back breaks the camel's back, then you'll think it's Mr. Uphill. If, on the other hand, you know what's happening to the pore pressures in the slope, you'll realise that if Mr. Uphill had caused it, it would have failed in 2022 because he generated lots of pore pressures, whereas Mr. Downhill has lowered the pore pressures and they're gradually creeping up year on year on year. Now, if Mr. Uphill hadn't built his garden, then it might still be there, right, for a few more years. But in fact, the real culprit was Mr. Downhill. And it's all covered beautifully in a paper by Bishop and Bjerrum as long ago as 1960. I was at school then. I'm looking around to see anybody here, apart from my friend here, who was actually alive in 1960. I didn't go to that particular conference. The school wouldn't send me. So here's another one. Here's another funny one. Right, somebody comes into your office and he's got a diagram. He's a well-known dam engineer, very, very prominent. And he says, Eddie, will you analyze this for me with a bit of software that you've written? And I say, yes, of course. And he promises to pay me, right, which is even nicer. So he says, unfortunately, it's not been built to full height yet, but it's moving. And we've actually built a little tow berm to stop it. And now we're not placing any fill because it's the winter. So can you do the stability analyses? And I say, great, what are the properties? He said, well, that's the rub, because the consulting engineer won't tell us, but we've sneaked a look at various reports, and we come to the conclusion that he's made a muddle. He's mixed up the core and the shoulder properties, and he's done some stupid stability analyses. This is the worst surface he can find, which goes 30 meters into bedrock, and he's got a factor of safety 1.3. So straight away, you know, he hasn't got a clue, right? And so we do a slip circle analysis. We got a good idea what the pore pressures are going to be because we've built to 2/3 height, and we've measured the pore pressures in the core, which is a high pore pressure zone. It's got loads of piezometers in it. And you do a slip circle analysis and you come up with a factor of safety of 0.7. Now you know that things are going to be in trouble. So you do it with a non-circular or compound surface, and taking everything into account and analysing the shear strength data properly and predicting what the future pore pressures are, you get a result of between 0.99 and 1.01. So you write a report, and what do they say? well, it's a two-word answer. The second one is off, right? So I'm sitting in my office, and then one day my friend rings me up, and he says, "Oh, there's a crack appeared." And I said, "Oh, well, I thought that we were going to build a bigger berm." He said, "Oh, no, we didn't. I thought we weren't going to complete the dam." He said, "Oh, we did." And I said, "Well, it's obviously failing, isn't it?" So, yeah. So there we go. I was right. And here's another little job from when I was in, less than half my current age. There's a breakwater in Bilbao, and it got storm damage. And the real problem is that this location here is where the big super tankers moor, but they can't get the oil ashore. So the super tankers go to Ireland, they tranship the oil into little tankers, and they bring it in to the nearer one of these where they can tranship it. And it's costing, back in the 1970s, £5 million a week, right? So who do they call? Well, they call some really clever people, clever hydraulic engineer, clever building manager, and they call for me because I'm the only one in the team who has a passport. So I get to do the field work. Now, what is wrong with this design of a breakwater? And the answer is nothing to do with slope stability, slip circles, non-circular surfaces. It's a material with a high friction angle. The real problem is that the armour in the critical section is 65-ton cubes. How big is a 65-ton cube? Well, sort of like this, yeah. And so, although it doesn't have a spectacularly high porosity, the pore size is huge. And so when the waves come up to the crest there, the hydraulic gradient through the 6-ton layer is colossal. And what does it do? It blows off the 2-ton armour stone on the lee side and starts to erode the rubble underneath. Yeah. Now, the process of washing out the 6-ton armour is called suffusion. The process of washing the flows in this layer, washing out what's underneath, is called suffosion. There are two forms of internal erosion, and they are simply not covered in any soil mechanics textbook that you care to buy. Okay, so there we go. Suffusion, suffosion. There are two forms of internal erosion, and that rhymes, which is great. So, what did they do? Well, we were working for the insurer, whose question to us was, if the whole thing is just built back to the original design, will it work? And the answer, you didn't really need to be good at geotechnics because the answer was no, it wouldn't. But so what did they end up doing? Well, they talked about having 85-ton armour, then 100-ton armour, and they finished up with 150-ton armour. Now, it's rather interesting because just down the coast in the Tagus estuary in Portugal, there was a breakwater damaged in the same storm designed by British consultants, and that used 18-ton concrete Dolos units. So if 65-ton armour isn't good enough, then 18-ton certainly isn't. So what they had to do was they basically had to not let on that there was a design fault, because otherwise somebody might even be shot. So during the site work, I was held at gunpoint for a while, which is pretty normal, really. It's nicer if you get your own bodyguard, but on this occasion, I wasn't smart enough to ask for one. But anyway, the Basques were in revolt at the time. No Basques here today? No? Okay, revolting Basques. So, the answer is that what they did was they went for a bigger armour. No need at all. They actually built this huge concrete structure to hold the wave wall in place, and this platform here lengthens the flow path length, and it reduces the hydraulic gradient by a factor of 3 or 4, which stops the internal erosion. But so basically, the designers and the constructors said the rebuild was completely essential, which it wasn't. No one must take blame, so they didn't. Money seemed to be no object. It was complete overkill because the answer It was very, very simple. Wrapped up the 6 ton there. Yeah. And how much would that have cost? But anyway, with those 2 last jobs, I bought my first Lotus sports car. Wow. Right. All yours, Paul.
Well, man, yeah, so yeah, isn't that other one? I think to go for that. Yeah, towards the right and one back to the left.
Ask me any questions you like afterwards when it's time.
Right. Good evening, ladies and gentlemen. Eddie's belied something that I always maintain: never give an old person technology. So if this goes wrong, it's not my fault. I don't know what.
No, you're on mine. No, you're on yours.
Right. My talk is is about earthworks. So if you look at the history of earthworks, you can probably go right back to Stone Age burial mounds, because people at that time heaped earth into mounds. The Romans didn't do a lot of earthworks because their roads followed the natural contours. And even the canals in the 18th century, which is sort of the first bit of major civils work, were generally horizontal with locks. So there was earthworks there, but they were not sort of cuttings and embankments as we know them. It was really with the advent of the railways in the 19th century, where to operate the railway, you needed a maximum gradient of about 1 in 50. So you then started to have to look at cuttings and embankments. And from one of Alex Kempton's papers, they moved 2 to 3 million cubic yards of material yearly between 1834 and 1851. Now you think of the technology then, it was horses and carts. That's a fair engineering feat. Once you come into the 20th century, roads have got a gradient usually of about 1 to 10 for major highways. So again, you're developing cuttings and embankments. You're taking material from cuttings, you're putting them in embankments. As I said, initially earth moving from horse and wagon, then you had steam driven plant. The picture there is side tipped, and that is a picture from the 1920s of the Edgware extension of the Northern Line. That's London clay. Why is it standing at 1 in 1? I don't know. Generally, there was no embankment foundation treatment, and you can always tell when an earthwork was built in Victorian times and they didn't treat the foundation, because what you'll see is the bottom third has a slope of about 1 in 10, because that's where they built it on the alluvium and it kept on failing. And they came back every night and built more of it. And there are embankments on London Underground. There's one at Chigwell, which is 10 metres high, which the top 8 metres is lightweight ash, steam engines. Because every time they came back in the early 20th century, they come back overnight and it failed again. You're putting London clay in. Now, Eddie's gone through some of this. Keep it simple, but if you think about the analysis of earthworks and slopes, it was all developed in the 50s and 60s. These things didn't exist. Anything like this. I used to give this talk with props. I didn't bring them with me today, but most people who were designing slopes were using log tables, and Eddie will remember what those are, and slide rules. That was it.
And you remembers those as well?
Yes, I'm sure you do. So what tended to happen was that people developed geometric constructions, and this is one from Ben Felanius, looking at the geometry of the most credible failure surface, because you had to analyse this by hand. Forget computers. This is taken from this is one of Bishop's and Morgenstern's stability charts. So you could just go to a set of stability charts. Which is what I've got there. Eddie's already said I wanted to focus on RU, because Eddie mentioned RU and said it wasn't something you should use. If you think about it, if you were designing one slope with slices and you were doing it all by hand, the only way you can solve a mathematical problem is to have one variable. So you've sorted out your bulk density. You've got three variables there. So you set C dashed and you set a parameter RU, which is the height of water or pore pressure on each slice. So that no longer becomes a variable, because you can take that away from the bulk weight and you've got the submerged weight on the surface. So that allows you to solve your problem, because the only variable then is phi dash. When you put RU into your slope stability program, it gives you a different failure surface 1,500 times. Every single one of those has a different phreatic surface because RU is a ratio between the height of water and the height of soil. Every single failure surface will give you a different number. Back to the safety. Again, Eddie touched on this. Traditionally, we'd use a lump factor. You'd work, and people still do. Believe it or not, around the world, it's still possible to do that, as long as you stay outside Europe. And usually you were looking at about 1.3. That was what the old Earthworks standard 2009 had. And you'd be looking at moderately conservative, or if you wanted to go worse credible, you could go for a lower factor of safety. And that's taken from one of John Perry's Syria reports. These were actually taken from London Underground, but as you can see, what he's suggesting is for a shallow failure, which is just affecting the side of the slope but not affecting the track, you can go for 1.05 for shallow, 1.1 for deep, or you can up the ante if you're looking at moderately conservative. I'm not going into too much of this because he's already covered some of these design approaches, but the problem you have is that my gripe against Eurocode 7 is designed from structural engineering. None of the people in here who took civil engineering degrees wanted to be structural engineers, or you'd gone and been a structural engineer. You didn't. You decided for whatever reason you wanted to do geotechnics. So why are they trying to force geotechnical engineers to think about structural engineers? Not how we're wired. And what you find is, and this is taken from a live job, people don't understand anymore what this old factor of safety approach did and how you could vary it at the end. So you have a situation on a major project which is being built at the moment where people have taken count of the Vado zone within 2 meters of the slope. They put an RU of 0.2 on it, a C dash of 0, and then they've applied Eurocode 7 partial factors. So that slope is designed probably at least 5 to 10 degrees shallower than it needs to be. I don't agree you should use statistical analysis for parameter selection, my own personal point, because we're dealing with things that God made, not with things that man made. You can work out rolling characteristic strength for concrete cubes because they come out of a production line. No soil comes out of production line. Eddie commented on water levels. People will take a flood protection scheme and they will put in a flood water level, and then they'll put it into Eurocode 7. So what they get doesn't even exist. If you look at a typical London clay slope, you might take Alex Skempton's parameters, C-1, 5-21. It's in enough papers. Skempton worked that out as a back analysis of just about failure. So effectively, it's a worse credible. And my strap line, and most grads at Atkins know that, designed for the worst credible, not the incredible. Think about what you're actually doing with Eurocode 7. Is that value that you're putting in, accepting the fact that you've already put a partial factor on it, actually credible? If you're designing a slope with a phi dash of 15, that's not a credible parameter. Eddie went through these. I'm going to go through them very briefly. Cuttings fail because of geological features. Pre-existing shear surfaces, Seven Oaks bypass and the M25 at Goston. Periglacial features in the Galt clay. And the M3 junction at Camberley ended up being built at 1 in 10 rather than 1 in 3 as designed, because it's in the Bracklesham beds and there's interbedded beds of sand and clay. And every time they created the slope, you got poor water in the sand, which took the clay away. So they ended up putting in drainage and building it that. As far as embankments are concerned, most of them tend to fail on soft ground because of lack of strength, or you could get the slope height geometry and angle wrong. Now, the two examples here, that one is a 4 metre high embankment on South Fraser Perimeter Road in Vancouver. It's failed on peat, and you could see here's the drainage channel at the side. That's gone completely and had to be dug out and rebuilt. This one is taken from the A12 Chelmsford bypass in the 80s. This is an old clay pit which they put washings in. So you had about 4 metres of soft clay here. The consultant who designed it got the contractor to roll blast furnace slag, 8-inch blast furnace slag in here to create a stable base. This is 25 metres. at 1 in 1.5, and it's now at 1. This is at 1 in 2, 2.5. It got to 19 meters and then it failed because the whole toe moved out as the soft clay squeezed. The embarrassing thing for the engineer, because this is the time where the engineer designed it, it wasn't design and build, was the site officers were on this side of the clay pit. And the contractor's project manager was sending a chainman down the village to get as many rolls of film as he could to take this click, 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 and he had a little cartoon book that he could flick through that showed this failure. A few more pictures of modes of failure. Some of these I just put in to make people smile. This one is quite serious. This one is on the Northern Line at Collindale in 1994. And you can see this is the southbound road. This is the northbound road, but it's disappeared. And this is failure in, this embankment was built. I showed you the picture of the side tipping train. This was built in the 1920s. Luckily, a track walker found it at 6 o'clock in the morning before any trains ran. As you can imagine, some train would have come up here and just gone straight off the embankment. This one I got from colleagues in Spain, which is quite a nice one because it combines natural and earthwork slopes. You can see somebody's obviously done an analysis and put a gabion wall in here to stabilise the toe. But what they've done is they've missed the fact that the natural slope itself is failing. So look, the whole gabion wall has gone because this is much more predominant mechanism than that one. This one over here is only because this is a very small failure. This is the Piccadilly line at Boston Manor on the branch that goes down to Heathrow. You can see there's a small failure here. It's affecting the track. If you count the number of people in high-vis jackets, you'll find there's about a dozen. But nobody's working and doing anything. They're all pontificating as to what may have happened. Construction on soft ground. We're dealing with normally consolidated soils or peat-type soils. If you build it too rapidly, you can get significant pore pressure increase, and it will fail. You've got three elements of the settlement. You've got immediate elastic, primary consolidation, and then secondary consolidation if you go over the pre-consolidation pressure, which usually with normally consolidated clays you will do. There is a temptation to accelerate the primary consolidation because the contractor wants it all to happen on a highways job during construction because he wants to build his pavement and he doesn't want to maintain it. But if you do that, you will get greater secondary consolidation. The problem you have with any calculation is that it's not an exact science. On the M74 completion on the southwest corner of Glasgow, it completed the motorway box, which was built about 10, 15 years ago. I looked at one embankment 3 different ways in terms of, go to the soil mechanics book, there's 3 different ways you can calculate settlement. I had a difference of 500 millimetres. This example here is from South Fraser Perimeter Road, which is the picture I showed you before of the peat failure. This was an interesting job because the overall client, it was built as a P3 scheme. The overall client was the province of British Columbia. And what the client did was built most of the earthworks on the 40-kilometre scheme before they let the main construction contract. So what they did was they instrumented all of the earthworks. And this here is showing you, this is showing you the fill thickness as it goes up. This is from rod and plate settlements. This particular stretch is about 200 metres. If you look at this, you'll see some of these are coming out at about 600, but others are coming out at 1400. So what's the right answer? Because if you were doing this as a design, you'd probably pick one section. So what's the right answer? At the end of the day, we didn't try and work out what the right answer was. What we did was we worked just on the settlement trend, where there's your primary, there's your secondary, you build it up again, more primary, and you're back to secondary. And it was agreed between all parties that when you hit the secondary consolidation, then you could build your pavement. They weren't saying, oh, well, the calculations say it should be 1,200 and we've only had 6. We'll have to wait for the other 6. It's never going to happen because it's not an exact science. A bit about quality control and specification, because I found over the years that people don't understand what they're doing. There are 3 types of specifications. There is a method specification. That is unique to ourselves in the French. Strange that we should We should have the same thing as the French. We don't usually, but there you go. Basically, that is picking a material. Once you've said that that material complies with what you want it to do, you're giving a layer thickness, a weighted roller, and a number of passes, and that's it. Look in the specification for highway works. You specify your material to table 6.1, you then go to 6.4. It tells you what you have to do for a particular piece of plant, and then your job is done. But most countries use an end product specification where you're actually trying to hit a percentage of maximum dry density. But as you can see, and I'm a bit of an anorak, I've collected a number there, those are all different. So they all probably, they all represent different local practice. Or you're into a performance specification where what you're looking at is the performance final part of the earthworks. Now, I've put ride quality, allowable bearing pressure. That one is a nonsense because anybody that designs foundations knows, depending on your foundation size, you have a different allowable bearing pressure because your stress bar was different. So if you specify 150 kilopascals, what does it mean? Nothing. Permeability of flood bund. I've looked at a number of cases in the last year where people have specified a material from the specification for highway works, an end product criterion of greater than 95% maximum dry density, and a maximum permeability. How the hell does the contractor know what he's trying to build? He doesn't, because you're mixing three different specifications. You either pick that one, or that one. You don't pick a combination of the three. Going back to the method specification, I've thought about this. The method specification in the UK was put together in the late 60s. That was the beginning of the big roads and motorways. It was put together with all the work, good work that the Transport and Road Research Laboratory did. And what it says is, if you compare, if you do what our specification says, you will get less than 10% air weight. That's it. Don't need to do anything else. But the problem is, over the years, in the late 80s, quality control came in and quality assurance. So people then said, well, how do we know it actually works? So you now end up with this horrible hybrid where the method specification works. Most of the motorway network in the UK is built to it. But if you do earthworks now, you've got to go out and do density measurements as well to check that you've got the density that you think you should have. You don't need to because you're testing end product when you've actually specified method. If you think about how that works, and particularly for granular soils, the standard Proctor test. Boy, is it a complex test to do. You've got a mould, you've got some soil, and you've got a rammer, and you stick the soil in the mould and you ram it, and you come up with a compaction curve. You know, this is super high tech stuff, and you design all your earthworks on the basis of that test. One of the other problems we have, of course, in the UK is there is a difference between what geotechnical engineers call fine soil and what materials engineers call fine soil. Because if you look at the standard specification, granular fill has to have less than 15% plain silt material in. If you look at BS 5930, it's 35%. So you may go out and classify a material from a borehole or a trial pit, as you would do as a geotechnical engineer, as a granular material. But a materials engineer wouldn't think it would be because you're not in this zone, you're in this zone here. This is a case in point from the A14. This is all terrace gravel material. If you look at this, your 15% line is in there. So if you're looking at that as a material, all these materials would class as class 1A granular, but these ones would be class 2. But if you're describing it geotechnically, here's your silt line, all of these would class as a granular material. So it's possible to fall down in terms of the way you describe it and how you should specify it. A quick slide on the reuse of the use of recycled and waste materials, because we're trying to save the planet. I think we are. And one of the reasons is because not only are we trying to save the planet, but it hits people in the pocket because you're paying £2 a tonne aggregate tax if you dig material and £3.70 a tonne if you take it to tip. or 970, 9670, these are last year's figures, if it's an active waste. So there's a lot of different materials that have been used. Traditionally, unburnt colliery shell, I put red and black blaze because this was on the M74 completion in Glasgow. We used over 1 million cube. PFA has been used for many years, but with the death of coal-fired power stations, that's going to be less and less. Construction and demolition waste, we used nearly 2 million cube of crushed concrete on M25 widening 10 years ago. There are other things like steel and blast furnace slag, glass sand. That embankment there is an embankment widening using glass sand. When we discussed it with the Highways Agency, their geotechnical engineer was worried that there could be cyanide bottles and you could get leachate coming out into a farmer's field. When I walked outside the meeting and said to the inspector, he said, "Don't be so bloody stupid, there's Beck's and Stella Artois labels on little bits of glass." There was a distinct whiff of beer for quite a few weeks afterwards when it rained. I've got a couple of slides on live load on Earthworks because this has bugged me for over 20 years. We take our loads from structural engineers. All the codes taken from structural engineers. Structural engineers consider that load as quasi-static and it's in direct contact with their bridge deck. If we talk about quasi-static, you're looking at load decrease with depth, a Buzinesque or something like that. This is taken from a position paper for the new Eurocode 7. And what they did was they went out to all the countries in the EU, including ourselves, even though we weren't in the EU anymore, and asked them for roads and railways, did they use a UDL? And if you look at this, the standard value is 20 in the UK. But if you work in Germany, it's 41 to 52. What's that about? It's 27 in Poland. If you go to rail, you've got equally. So, you know, this is a guess. Nobody knows. They're just structural engineers making it up. And I've said as well to structural engineers, they cop out because at the end of the day, all the loads they look at as live load, traffic, wind, thermal, if it's a structure with no bearings, they're not actually quasi-static at all. They're all cyclic. But that's too difficult a problem for structural engineers to solve. So they call it quasi-static. Everybody's happy because that's what the code says, and off you go. This is an example from a haul road in Kazakhstan. Sounds a bit innocuous. What a haul road? It's 45 kilometres long, and it took modules like that. That's the size of about 30 London buses. It's on a multi-wheel trailer, 60 metres long by 12 metres wide. We had areas of normally consolidated clay because this is right next to Caspian, up to 4 metres thick. And the client decided he wasn't going to treat the ground, but he would put in the pot 25 million as a maintenance provision. These modules were up, gave a ground bearing pressure as a UDL of 70 kilopascals. Way above what you'd look at for a traffic loading. So we actually designed a dynamic embankment trial, which comes on the next slide. But if you look at this is from Plaxis analysis of that embankment. So you can see we designed an embankment trial to run a 20 kilopascal, 40 kilopascal, 70 kilopascal UDL. And you've got various types of hardening soil model here. And what you can see in terms of the vertical displacement is by the time you get to 70 or 120 millimeters. If you look at the pore pressure, you're up to 70 kilopascals pore pressure. Here's the vehicle that we actually used. A smaller one, 25 by 8 meters. This is nearly every crane counterweight on the site at the time because, of course, they weren't trafficking anything. We ran a number of passes, 20, 40, 70, up to 12 and back down again. And these are plots of the pore pressure taken from piezometers, vibrating wire piezometers installed in the soft clay with time. So you've got vertical displacement and pore pressure change here. The maximum pore pressure change was 6 kilopascals on a 70 kilopascal load. So it's going somewhere else. It's either transient and never gets there because it's not simulating a big Buzinesque pressure bowl at the bottom, or it's actually taken, this was the construction of this embankment, was about 1,200 of local uniformly graded sand with capping layer 300 on top. It's actually taken out in the capping layer under individual tires. So that much pore pressure settlement was about 25 mil max. So all of that good finite element work, totally wrong, because all the assumptions are wrong. I've got 3 final thoughts. This is a bit cynical, but this is something for you to ponder. Okay, this is a possible glimpse of the future. All your ground investigation data is now electronic. It's all in AGS format. That man and me grew up with hard copy borehole logs. He's thinking about it now, I'm cringing. You take that design data, you extract it and put it in a spreadsheet. You create a design line graphically and you play around with the geometric fit on your graph and you assign a characteristic value. You put it into slope stability program and you generate 1,500 failure circles and you record the minimum one in a report. Where's the fun in that? You've all become automatons. You switched your brains off. A couple more. These are 2, this one and the next one are a couple of questions that were asked to John Burland in 2013. So they're quite prescient because we're nearly at 15 years. First one, future of geotechnical design, what theories and tools? It's as much a craft as a science and will always remain so. A craftsman knows his materials by working with them. My father was a tailor. When I tell you this, you'll go around looking at people's suits. A well-made pinstripe suit, all of the pinstripes match on the shoulder and they also match on the lapels. If you look at most pinstripe suits, they're either manufactured quickly or they're manufactured by machine, and they don't. Because my father understood what the cloth he was working with. We as geotechnical engineers need to understand the ground. You know, the same message that Eddie gave you. It's essential that future geotechnical designers are not seduced by the ease of computer modelling. I've got one slide at the end that actually gives you an example of that. That's the second one as a fair mail message from John to you guys in the room. Yeah, combining the traditional skills. Materials are complex and laid down by nature. So modelling their properties is challenging than more modern artificial materials. The last slide I'm going to show you, I, like Eddie, review technical articles. This particular one was from the ground improvement proceedings of the civils. The job was oil tanks on soft ground, and the design had been done in Plaxis of vibrostone columns. My question was, table 7 indicates stratum 2 CU is 15 kilopascals. This is below a minimum value to ensure lateral restraint surrounding soil and hence is unsuitable for the installation of vibrostone columns. The response I got, authors are highly thankful to the reviewer for this comment. Authors would like to convey, during numerical modelling of the stone columns, no such difficulty was found. No shit, Sherlock. Does that mean it works just because you can model it? No, because a model is just a model. It does what it says on the can. Thank you very much.
Hello everyone. Last talk. So my name is Matthew Bowes. I've been working on HS2 with Covey over the last 3 years, and I've been focusing primarily on the field trials, which has been very interesting for me. And just to cover what I'm going to talk about now is the earthworks and their significance on HS2 quite quickly. Go into some of the requirements that Paul just talked about in terms of what we had to comply with for earthworks for high-speed rail embankments. And then I'm going to delve into a particular trial that we worked on, the Great Worth Field Trial, which comprised of lime stabilised glacial till. So HS2 and earthworks. So as we're all aware of, probably HS2, and it's a huge project, and coming with that is it's the largest earthworks project in the UK currently. I've been focusing on the C2, C3 section, which is the central section, and that's about 80 kilometres long, and estimates of about 30 million metres cubed of material have to be moved for the construction of this. And just to put in some standard volumetric measurements, we've got 12,000 swimming pools equivalent, 30 Empire State Buildings, or 15 Great Pyramids. And with Earthworks, because they make up such a large component, they make up a large component of the cost as well. And furthermore, most infrastructure projects do have quite a toll when it comes to carbon emissions and Earthworks, with most projects making up Earthworks making up about 20 to 40% of most carbon emissions for infrastructure projects. And therefore, some of the decisions that we make as engineers can actually have quite large impacts on the sustainability of the project. So some of the key considerations that we need to make, obviously, is the type of material. Is it correct for the job, and whether it's safe and stable when constructed for purpose? We need to consider where that material is coming from, and we also need to consider the amount of material that we have. And then furthermore, with the site, how big the site is, how are we going to handle that material, and where are we going to store it if we're limited for room? And overall, all of these decisions then can have large impacts on sustainability and cost. So once we've decided those materials, we obviously sort of have to communicate them with the construction side and specify how those earthworks are going to be built. And as Paul alluded to, the Series 600 is a common document that's used to specify most earthworks projects in the UK. And one of the tables that I had quite a lot of involvement with the field trials project was the table 6.1. And I break it down into sort of three simple ways, three simple sort of components that explain the whole table. The earthwork has to be the correct material for the job, it needs to be in the correct condition, and then it needs to be constructed in the right way. So just as an example, I've got a class 1A1 material here, which is a granular fill we use for HS2. And the first few columns just outline basically, is it the correct material for the job? And we specified a limestone in this case. And therefore, if we got a limestone and we don't have any other constituents in it that we don't require, then it's good to go. And then the next part is checking whether it's in the right condition. And the next section basically specifies a number of tests that we use to check that it is in the right condition, including moisture content, slate durability testing, and various other tests. And then the final column then highlights what the construction methodology required and the checks that we need to make sure that it's being constructed in the right way. And as Paul alluded to, in the case of HS2, we ended up having a combination of end product performance, which was the compaction and air voids, and then design performance, which was specified by HS2. So alluding a bit more to that purple box that I highlighted on the previous slide, a lot of the design performance came from the technical standard for Earthworks, which was a document provided to us by HS2. And basically within that, there's a series of parameters and performance criteria that we need to show and demonstrate with any earthwork fill. And these cannot be changed by the designer. These are fixed in stone, and the document is there to try and ensure that Earthworks is consistent across the whole of the project. Two of the key criteria that I was focused on was the static performance, which was where we were measuring we had to ensure that the upper embankment fill for any earthwork embankment was exceeding 60 MPa using the secondary surface strain modulus, which is similar to a plate load test. And then the second one, I put that animation in, hope you liked it. The railway velocity had to be 1.6 times the design speed of the train. And this performance criteria is quite critical when we're dealing with high-speed rail, because if the train starts catching up with railway waves, it then creates essentially similar to a sonic boom, but in the ground, and we get interference and amplification, and then it can degrade our embankment more quickly. So we had to ensure that the earthwork performance allowed the railway wave velocity to pass through the ground quick enough. However, another clause in the technical standard was allowing the designers and the contractor to trial alternative materials, provided that we passed the design performance that I just mentioned, and also if we do prove that material works and passes the design performance, we had the opportunity to maybe suggest alternative compaction requirements for the fill. So then this opens up a lot of questions of, well, can we use Site 1 fills? And Site 1 fills are definitely beneficial to most projects because it has a lot of benefits. And one of them is that the contractor has more direct control over the compliance of fills. We've got immediate availability of the fields, which allows potentially allows the project timeline to be accelerated because we're not dependent on any other sources. It simplifies the logistics because we don't have to plan about mass haulage schemes across the UK from importing materials from afar. And that has huge environmental and cost impacts because we're not having to transport all of that material very far. So across the C2, C3 scheme, there was a number of different cuttings where material was being excavated, and we identified that some of the materials coming from these cuttings could be used for high-speed rail embankments. These are a few examples. So we had some iron-rich limestone based in the Chipping Warden Green Tunnel, which we considered could potentially be used as a Class 1A1 granular fill. And then we have the Finmere area where there was a substantial amount of glacial fluvial deposits, which we considered maybe cement stabilizing and that being allowed to be used as a transition fill. And then the Great Worth Green Tunnel, which I'm going to focus on now, was a large cutting where a significant amount of glacial till was identified that we could use. So being a glacial till, you would probably anticipate that it isn't actually very suitable for earthworks fill by itself, and it needs to be modified to reduce the plasticity and improve the strength and the stiffness of the fill. And this is just some pictures of the material as it's changed, sort of using that lime stabilization process with my size 10 foot per scale. We've got some glacial till there untouched, and then we've got some stabilized and pulverized material there in the middle, ready for compaction. And then once we've compacted it with a roller, you can see that it's quite the transformation. And the benefit with lime stabilization is that there is a number of reactions that go on in the material that can improve its strength over time, one of them being a pozzolanic reaction. One thing we did have to consider, though, was the sulfate within the glacial till. This is quite a problematic issue for earthworks, and previously a case study, which is quite well documented, the M40 case study, was where they mixed the clay, lower layers clay, with lime and water, and that had high sulfates. And that basically led to significant swell in the material, and that was caused by expansive minerals. So the two primary suspects are ettrinite and thormosite. So to combat this, the Series 600 Earthworks, in its standard form, recommends that the total potential sulfate should be kept below 0.25% to limit the risk of any swell happening in the material. So we had to then go ahead and check across a number of cuttings where glacial till was identified, whether that total potential sulfate was low enough so that we could use the material. And from all the testing across multiple cuttings, including the Great Worth Green Tunnel, which is the one where we completed the trial, we could see that most material in the top 2 meters of the glacial till had very low sulfates, with a couple exceedances. However, most of the material that was tested below that you could see elevated TPS content, and therefore we decided that anything above 2 meters below ground level we could use. Another consideration before doing the trial was whether we could reduce the lime. And again, in the standard, the Series 600, 2.5% lime by weight is often sort of the prescribed amount of lime that we should use. However, a lot of recent research has suggested that we could potentially reduce that lime content and still achieve the design performance criteria, provided that we gave it enough time to cement and improve its strength over time. And there's also a bonus of if we're limiting that lime content, then we might also reduce the risk marginally with the sulfate swell minerals, because we're reducing a component of that chemical equation essentially. And this, again, if we could reduce the lime, has opportunity for costs and carbon savings. So at this point, we decided that it was worth exploring, and we went ahead with some testing, and we undertook the Great Worth trial embankment. The objectives were firstly to classify the material in terms of grading and its sulfates, which we'd in part done beforehand. And then with the trial, we aimed to then assess the design performance criteria, so the static and dynamic performances that I talked about a minute ago. And then if proven, we'd set the compaction criteria, or at least keep it the same as what was already prescribed in the technical standard. And then the bonus objective was to reduce the lime binder. So this is a setup of the trial embankment. It comprised of 12 250 mil compacted thick layers, with the bottom 6 comprising of glacial till with 1.5% lime. And then we benchmarked that against the standard of 2.5% lime. Then alongside this, there was a suite of testing that was completed to verify multiple things. So we had a suite of different geophysical testing. We had some classification testing. We had some nuclear density gauge testing and core cutters to look at the compaction of the fill. And it was a very big embankment. It's 50 meters by 30 meters, which is quite a novelty in the UK. So the construction process, relatively simple. The material was hauled from the cutting, which the cutting was only a couple of 100 meters away from where the field trial was undertaken. Then the material was spread. And then at this point, we need to check that the material is in the correct moisture content range for compaction. And we do that using the moisture condition value. So the graph to the right basically shows the compaction curve of the that was determined in a lab with the glacial till with lime mixed in. And we needed to achieve that maximum compaction. And you can see that the moisture content there's a window of 15 to 19 roughly to get that kind of 95% maximum dry density. However, when we're constructing the material, and particularly with lime, the moisture content test isn't too ideal because it takes time. It takes 24 hours or so to do an oven-dried moisture content test. And therefore, we substitute in the moisture condition value, which is a quick test, which is inversely related to the moisture content. And in doing so, we can check that the material is in the correct range of moisture content by looking at the MCV, which we targeted to be about 10 to 12. And then once we were obtained that MCV test and we could see that the material was in the range of 10 to 12, we'd then give the OK and we'd go ahead and start stabilizing and compacting the fill. So this is the process then of if the material was too dry, we'd add some water, which was particularly the case for the 2.5% lime because we had some very hot weather at the time. We spread the lime then with a tractor, and then we pulverized it with this machine called a Vertgen on the right, and that was that pulverized the material, as the image you saw earlier. And then at that point, we checked the MCV again, ensured it was okay, and then we gave the driver the thumbs up to compact it, and we got a lovely finished embankment surface. So then at that point, we got the surface, we had to undertake the testing, and we got an example of the EV2 strain modulus testing there on the left. We've got some MASW testing there in the middle, which that was completed on the foundation and not actually on the embankment itself. I just didn't have a picture, so that's why the surface looks a bit different there. And then on the right, we've got some density testing of the nuclear density gauge. So once we compiled all of that information, we had to start looking and first ensure that we were passing the design performance criteria. So the graphs on the right basically show the bottom 6 layers, the 1.5% lime and the 2.5% lime, and how that EV2 value basically changed over the first 48 hours. And you can see generally there's quite a steep increase, but the spread then it kind of levels off, although there is quite a bit of scatter in the data. Interestingly, we observed that the 1.5% lime was performing better than the 2.5% lime, which is not intuitive, which I'll get to in a little bit more in a minute. However, the 1.5 lime and the 2.5 both exceeded this 60 megapascal criteria that we needed to achieve, and therefore we decided, well, what's the point in adding 2.5% lime in this case? But obviously we had to look at the dynamic performance as well. And this is an example of some cross-hole geophysics that's completed through the embankment. And we basically had a confidence limit, or the criteria there marked in the red line. And we could see that the cross-hole was showing that the dynamic performance was exceeding the requirement. But again, you can see that although it's decreasing between the 2.5 and the 1.5% lime, the 1.5 is again still exceeding that requirement. And therefore, at this stage, we decided to go ahead and use the 1.5% lime. So, determine the compaction target. So at this point, we decided to go for the 1.5% lime. So we assessed that data and we looked at it to determine that 95% compaction would be suitable for the earthwork fill. And we targeted that the air voids must be less than 8%. And just interestingly in the data, so these points are basically the average dry densities per layer with that against that average moisture content. And you can see that with the 1.5% lime, we've nailed the moisture content pretty well with the MCV test. However, with the 2.5, the material seems to be quite a bit wetter. And the reason for that being is that although the 2.5% lime during the hot weather, with the reaction being exothermic, we thought that we were going to be losing quite a bit of water. And therefore, I think we overcompensated with too much water during that part of the trial. And that led to the layers being too wet, and therefore we didn't compact it as well. And that might in part explain the reason why the EV2 testing was partly reduced as well in the 2.5 relative to the 1.5% lime. And then from all of that, we then updated the table 6.1 with the updated compaction requirements and the air voids. And we confirmed that this glacial till could essentially be used, which we then sent off to HS2, and Paul approved it, I think. That's new enough. So, and so overall, the field trial was really good. And I think spending the money and doing these trials beforehand can really add benefit. And this demonstrates it. It enabled 300,000 meters of cubed of material to be used, which is replacing imported material, which is a significant cost saving. We managed to reduce the lime binder across the whole scheme by about 30,000 tons, which again had a huge carbon saving. And collectively, that reduced the overall C2C3 carbon equivalent emissions by 170,000 tons, which compared to the anticipated and preempted carbon emissions that we were going to produce from completing HS2 and C2C3, actually reduced the carbon equivalent by about 8%, which is a huge saving. And then that also led to significant cost savings as well overall. Yeah, thank you very much. Thank you.
Thank you very much to all our guest speakers. So now we'll open up for your Q&A session. So if you have got any questions for those in person, you'd like to raise your hand. Or if not, for those online, you can scan the QR code for Slido, and then we will help you to ask your question. Yep. Anyone in the room?
I'd just like to say something about it.
Yeah, sure.
That showed the MCV test. In my larger Earthworks talk, I talk about that as well. If you look at the way that the acceptability of adhesive soils has developed over the years, it's changed. Go back about 20, 30 years, and it was all based on moisture content. Acceptability was based on a multiplier of plastic. So depending on the plasticity, the clay high plasticity 1.3, low plasticity 1.2. That alluded to the fact that if you use that as your criterion, think about how you test it. You take your sample as the contractor dumps the material to compact it, and the first thing you have to do is dry it out, because you need to find out the moisture content. Having dried it out, you can then re-wet it and roll your little thread for a plastic limit, and then you put it back in the oven again. So by the time you've gone from sampling it to getting the test result, is 2 days. By which time the contractor's put another 2 meters of fill on, and if it's unsuitable, you can't do anything about it. The great advantage of the moisture condition value test is you put it in a mould and you drop a hammer in a jig. Matt showed a picture of it, and you get an instant result. The only thing that I would question, and when I first used it, and it shows how old I am, it was on the ground investigation for Blackburn Southern Bypass, which was 1989, when it was in its infancy. And what we actually did, and it's not something that's in the British Standard, it's something that I disagree with. We tested the remolded shear strength in the MCV mould, because you've got a sample in a mould, you've compacted it. All you need to do is put a shear value and test it. And what that gives you is that gives you a relationship between MCV and remolded shear strength. Now, if you go to the literature, what you find is for 2A, it's 8 to 12. For 2B, it's 12 to 16. 16 you won't get, because even now, Earthworks plant can't compact it. That's moisture content of 16. But you're wasting a lot of material if you use the 8. On Blackburn, the glacial tills on Blackburn Southern Bypass, we got it down to 6.5, based on the fact that we were trying to meet a minimum undrained shear strength, remolded shear strength criterion of 50 kilopascals, which at the time is what TRL had said you required so that you, when you compacted the layer above, you didn't create ruts in the layer below. And also, when a lot of the research was done, there were a lot more motor scrapers in the UK. Now most of it is done by back actors and Volvo dumpers, and it was the optimum speed that a motor scraper could go if you could keep it over 50 kilopascals. So again, you know, when you think about specifying earthworks, think how long it takes to do all the testing to get it to comply. Because if you pick something, I mean, the other test that was used was hand shear bone. Now, I'm old enough to have worked toward the back end of the M25 construction between Junction 6 at Godstone and what's now Clackett Lane Services, but was called Western when they built it. And that was all done in the Galt clay, very high plasticity. So if you went to the specification pipeworks, specification road and bridge works as it was then, it was still the same, greater than 90% liquid limit, it goes off site. That would have meant that whole job would have taken all the material off site and had to import it, which wasn't practical. So the method they used was a combination of moisture content and underarm shear strength with the shear vane. I actually went back through at the end of the job and looked at all the records because I worked for a contractor, we were putting in a claim in, and every single shear vane was greater than 120, which meant the inspectors fiddled the results because they put it in the ground and they went like that, greater than 120. Probably a lot of those results were less than 50 kilopascals. You would ever know because it's all buried.
That's interesting. Yeah. We do have a question in Slido, but I'm not sure who is directed to, probably towards Matthew. So the question asks, which BGS geology layers, apart from the London clay, has caused the most issue for you?
Well, for me, I haven't worked on the London clay in the sense of the earth.
Apart from the London clay.
So apart from that,
anything
well,
else?
I'd say probably being so young in my career, the glacial till definitely is quite complex. It's an amalgamation of everything across the UK. So it's consolidated. You don't know what you're going to get. It varies from place to place. Sulfates are a big issue with it, with foundations and glacial till covers a vast amount of the UK, particularly the outflow parts in the glacial. So I would say that it's a huge part of engineering and what we do as civil engineers working typically on the surface.
The thing I'd add to that is glacial till classifies as cohesive soil, 2A, 2B. No, it classifies as 2C. It classifies as cohesive soil, as any other over-consolidated clay does in the UK. Any geologist would know it's formed a totally different mechanism, and it is a totally different material. And you cannot compare it with Oxford clay or London clay or all the other over-consolidated clays that were formed in the marine environment. You have to look at it specifically on its own merits.
That's nice. And I do have a question, if no one else has. Paul and Eddie alluded to the fact that engineers need to be careful when using EC7 to design geotechnical structures. So do you have any good piece of advice you could give to?
I will give one piece of advice. If you've looked at the Earthworks book that I wrote with Peter Gilbert, there is a chapter in there on factors of safety.
Yep.
And Peter was in our Birmingham office and I was in our Epsom office, and this was before lockdown. So we were on the phone. Teams didn't exist. And we spent half an hour debating one particular paragraph. I think it's on page 270, as to how we should define, how you should work out for earthworks factors of safety. And our conclusion was design it old school and check it for Euro Code 7 if the client wants it, because then you have the flexibility to do whatever you want. And going back to what I said about structural engineers in Euro Code 7, I'm a geologist, I don't count. As the geologists in the room don't count, even though I prostituted myself to geotechnical engineering. I've asked civil engineering graduates, you had a choice of what you wanted. You did a civil engineering degree, you had all these opportunities available to you. You could have structural, transport planning, you could have highway pavement, you chose geotechnical engineering. And the general consensus I get for people's answer is I wanted to play with numbers and think outside the box. And that's what makes us tick. So don't force us to be structural engineers who work to structural codes. The other thing I'll ask, the other anecdote I'll give you, I gave a talk I was asked by our head of building structures in our London office to give a talk to the graduate engineers. And I put a slide up And that slide had 2 lines. And it said structural engineer to geotechnical engineer. Why can't you give me a definitive design value? Technical engineer to structural engineer. You surely don't expect me to analyse 280 load cases. That is the different mental attitude that we bring. And it's a case of bridging that gap. It's not a case of forcing one discipline to work in the field of another by a particular design approach. So my advice would be, do it SLS, have a play with it. Enjoy yourselves, because what I put up in that slide as my view of the future is the Eurocode 7 automaton. You know, you'll suffer brain death. We didn't, you know, he and I didn't join this industry because we wanted to suffer brain death. We wanted to enjoy what we did. And I mean, sad individuals that we are, we have done. So, you know, that's the message to you. Do the same thing.
Yeah, well, I've got some answers to that as well. And I would just like to echo that. Do it the traditional way. And then afterwards, if you have to, do the EC7 check to satisfy a client's requirements. Now, EC7 has a lot of rubbish in it, but it also has some very, very sensible things in there, right? And one of them is that it talks about geotechnical problems falling into 3 classes. So there is no reason why you should do slip circle analysis with 1,500 circles on a flower bed, right? This is something that you do with traditional custom and practice. And I'm a big fan of YouTube videos of people restoring historic buildings. And there's this chap called Josh Harvey who builds dry stone walls. And this morning I was watching him building a dry stone wall for a retaining wall that high. There's no way that you can do an earth pressure calculation and show it stands up.
It's got
right?
no shear capacity.
No, absolutely not. Now, there are 3 design approaches. And remember that back to who's a civil engineer by original degree and who's a geologist? Right hands for civil engineers. Yeah, left hands for geologists. Right, okay, good. So there's three ways that we analyze things, and they correspond to the 3 design approaches. If you think about how we design footings and piles, it's load over failure load. If we think about retaining walls, it's active pressure against passive pressure. And when we deal with slope stability, it's factoring the shear strengths. So these correspond to the 3 design approaches. And a good thing about EC7 is it tries to harmonize the 3 approaches. Doesn't work for slope stability because we can't do it like a retaining wall. We can't do it like a footing or a pile. We can only do it with the factored properties. And so if you pre-factor the properties, there are cases where you will get the wrong answer. So don't do it the traditional way and then afterwards do an EC7 check. Right?
It's as much as anything else because it's a more pleasurable intellectual exercise.
Yeah,
to play with it.
That's a nice way of looking at it, Paul. I do go along with that. But the third, the category where EC7 applies is in the middle, because the really, really interesting cases fall into the category where EC7 doesn't even apply anyway, right? If you are trying to stabilize the big Folkestone Warren coastal landslide, you will never get a 25% improvement on the factor of safety from the one it currently has. Why? Because we don't have enough money. We can't build far enough out into the sea. We don't have the materials. So the problems that I really like are the ones where EC7 doesn't apply anyway, right? I have my favorite type of slope instability and my favorite types, and they fall outside the remit of EC7. And my guess is, because I didn't like it when at Arabs, I worked in Ken Cole's group and had to do foundations. I hated that. I liked slope stability with Mike Bailey, and I sort of tolerated retaining walls. But you know, and those 3 categories are very, very interesting because there's Josh Harvey building dry stone retaining walls, you know, could quite capable of killing somebody if they fall over. And you know, and I just asked myself, should he be allowed to do that? But if he could argue the case, he'd probably say it's outside the remit of EC7. And I find retaining walls really fascinating because, of course, you've got any gardener can build a retaining wall that high, right?
Try and analyse it.
But as you get taught higher and higher, any geotechnical engineer can probably design a retaining wall the height of this room. But if you go 4 times the height of this room, because the strains are so much bigger, you really need somebody who spent their life doing retaining walls to get it right. Yeah. And slopes are a bit like that. The routine stuff for small embankments is, yeah, anybody can do that after the fact. But, something that's 40 meters high, yeah, that's getting a bit, a coastal cliff, which has got a landslide in it, it's 150 meters high. That's really, 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 really tricky.
One other thing I was going to share with you, it's a reflection I've had over the last 5 or 6 years, and it's very biased against civil engineers, unfortunately, being a geologist by degree. And that is, I've sort of reflected on design parameters and how we obtain design parameters. And the conclusion I've come to is that either consciously or unconsciously, civil engineers work with materials. So they work with steel, they work with concrete. Oh no, look, they've got the soil to work with, so it's a material. So they look at the material and they analyse the material to death. But the problem they've got is exactly the slide that Eddie showed you, that in one U100 sample, you could have 2 different materials. So it begs the question, why analyse it to death? As a geologist, I was taught how sediments form and their environment, and it's heterogeneous. And the example I give, how many people here use SPTN values to derive other parameters? I see a lot of nodding heads. Okay, how's an SPTN value taken? You take a capable percussive rig, you set the tool up with the top hammer, the SPT down the hole, on some drill steels, and the driller appears and he's got a stick that long, and it's got on it white marks in paint, 75mm increments, and he gives that to the second man, and the second man puts it on the casing, and with a thick piece of chalk, he marks 75mm increments off the stick. And the driller goes behind the rig and he starts dropping the hammer on the clutch. And the second man's watching and watching and watching. And that very thick line gets to about the top of the casing. And he does that and the driller makes the number down. And he does that 4 times over and there's your SPT. So what's the point of turning it into an N60? Because the test itself is so simplistic. Why overanalyze it?
Yeah, Paul, another thing is we don't even do it properly. Because you're supposed to do it not with a Shallanova rig, but with an American rig which does wash boring, and that's where a good proportion of the correlations come from, and they are different. It's like if you do liquid and plastic limits with a Casagrande cup, then the rubber base has a different stiffness in the UK according to the BS than it does in the Americas. And therefore, if you read an American paper, you will find a different correlation. There's some things that I absolutely detest with a passion of certain politicians. Okay, if we forget that, right? But one of the things I detest with a passion is completely nonsensical technical papers. Right? There is a paper by the distinguished Professor Skempton, who even has an Imperial College building named after him, where he suggests that you can use a factor of safety of 1. Completely insane. It's fine if you don't mind a few failures or a lot of failures, but it's insane. I absolutely hate the papers where people have flown a drone or an aeroplane and they've measured slope angles and they've assigned a score to that, and they've assigned a score to something else, whether it's tree covered, and they come up with a map that has different coloured areas, some of them red, right? And that tells you where the geotechnical hazards are. I absolutely hate those, the red area papers. I hate the papers where some MSc student has done Plaxis analysis or something else like that, and they've tried to make it a sort of world-shattering paper out of their MSc thesis. I hate those papers. I like papers where I learn something. Now, I want to tell you, because we all went over time, didn't we? Did we all go over time?
Yeah, we still have.
Yeah, yeah. I was with a friend of mine down at the Lago Sereno in the Tow part of Italy. This lake is held behind a landslide block which is moving, right? And my pal I was with, who's an engineer and geologist, wanted a contract from the local authority. So we got involved with the mayor of a town which is about 500 meters below and 2 kilometers away from this moving lake dam. And my friend Gino said to him that he would produce the hazard map. And the mayor of this town said, look, I know what the hazard is. I know where it is. And the last thing I want is a map with red areas on it. And I thought, yes, you're my sort of man. Because he said, what I want is somebody to do something about it. Well, it's Italy, so they didn't.
I was going to share another anecdote, and I've tried to find the TRL report, but it's so old that I can't find it. I can't even Google it. But at the end of the 70s, the TRL ran an exercise where they took a large block sample of clay, but it was no consolidated clay. And at the time, most of us who now work for consultants wouldn't have worked for consultants because consultants' geotechnical departments were very small. Ground investigation contractors did all of the investigation and then would do the interpretation. And they had massive labs. So the TRL subdivided this very large block sample and sent bits to all of the major contractors' labs, asked them to do plastic linen testing. Simple test, you dry it, you wet it up, you form a thread on a piece of glass. What can go wrong? The variation on the moisture content for the plastic limit on the same sample, accepting the fact that there may have been some heterogeneity in the cell, 30%. So what that says is that a basic person doing a simple test won't necessarily get it the same as the next person. So when you look at results and you start playing with them statistically, they're so riven with mistakes anyway, why bother in the first place? And that's a geologist speaking rather than a civil engineer speaking.
Yeah, and this is another thing. If you get a site investigation report and there's some graphs in there and they are smaller than the area of the page devoted to logos and stamps and government authorization, you know that the results haven't come out of a test at all. They've just been invented. They're nonsense. Right? I've done enough work in some dodgy countries to know for that to be a fact. And here's another thing. I did some work in Georgia. We had a borehole. Right? The thing was logged in Georgian, and it was translated into English by the head of the site investigation company, who nobody dared question because it's ex-Soviet. You know, nobody does, because otherwise they might never get a job, certainly because they'd be missing an arm and a leg. And of course, there was no guarantee that it would even been translated correctly. And I think that's bad. In this country, I've seen very, very expensive coring done. The core boxes logged properly by people who write it down. They then go into an office. They write it neatly onto borehole logs. They give that to a secretary. The secretary types it up. And it comes back and they compare it to their log that they've written. Don't compare it to the samples. Don't compare it to even what's in their notebook. What guarantee is there that it's correct? None. Fortunately, the job didn't get built. But these things are much more fundamental than you'd think. And I learned a lot from Paul and even you today, with differences of approach. I started out wanting, and this is for you, Paul, I started out not wanting to be a geotechnical engineer. I couldn't see the point in it. Right? I worked for Freeman Fox and Partners, and I worked on a bridge where the criterion for the piled foundation for the piers was zero settlement. Anybody who can say that has not got a brain cell, right? Because the steel structure deflects. Why doesn't the foundation, right? And I fell out with the boss because I didn't like the way he ran the office, and I thought there was a problem with the concreting sequence on this bridge in Australia, and I got the sack basically. But when it fell down, it killed quite a lot of people. And on the subject of killing people, it is a hideous job to try and decipher a trial pit log taken from the pockets of somebody who was killed on site. It is horrible, right? You want to think, whatever you do when you're on site, safety, safety, safety. People around you will be getting away with the most cavalier things, but for God's sake, think about it. Now, 3 of the people I worked with in the geotechnical division at Arup, which is where I found my next job after that sacking, were killed. 2 of them on site, John Mitchell and Chris Bailey, and Mike Bailey, who fainted at the sight of his own blood and had nearly killed me in his car by fainting at the wheel on a motorway because he cut his hand on a bit of barbed wire. He fell in front of a metro train in Paris and was killed. So I think pretty much the same. He always used to stand right on the edge of the platform. For God's sake, don't do dangerous things like going down unsupported trial pits or any of that sort of stuff. Think all the time about safety. The slope stability, the compaction, the materials, they don't count. Your safety does. And I will remind you that what happened at Carsington when they used carboniferous limestone in drainage layers and pyrite-rich mudstone in between was the pyrites oxidized. It hit the limestone drainage layer and generated a lot of carbon dioxide. The carbon dioxide collected into a sump, which was intended to measure the seepage when the dam was in operation. 2 guys were in there cementing a V-notch weir to measure this flow, and they were overcome by the carbon dioxide. 2 more men went down to rescue them. They were also overcome. There were 4 people who were killed by carbon dioxide settling into a sump that was less than the height of this room. So there are certain things out there on site which are very, very dangerous and we don't think about. So please think about safety all the time.
Thank you very much. So I think we are at the Q&A session over here. If everyone can join us giving a big round of applause. Take a note of thanks. The BGA ECG will be providing a note of thanks, which is sustainable plant launches to all of our speakers, which I'll hand out shortly. Yeah, and also a huge thanks to our series sponsors. So, and also do stay tuned on our website, and we do have a lot of future sessions coming up of the MOGE discussion series. And just some announcement before I let you go. So the call for abstracts is now open for the Earthworks 4th Biennial Conference next year. And after that, we do have a joint meeting between the BGA and the International Geostatics Society coming up on the 24th of September. And we also have the BGA Special Conference on the 15th of October to mark the event of the 75th anniversary for the BGA. And we will also be having the cooling prize on the same day, followed by the BGA annual dinner. And it's worth noting that for BGA ECG members, the ticket price for the BGA dinner is only £40, which is much less. And lastly, we do have the BGA Early Careers Program welcome networking event in October. So if you are free to join us. And lastly, a big thank you for all of you attending in person today. And if you are free later on, do join us at the pub, the Alice, and there'll be food for everyone. Yeah. So thank you, everyone. Okay.